So, here is a small network and let us read it and try to understand. So, this is the network given. The potential of the point A is given to be 70 volts, that of the point B is given to be 0 volts and of C is given to be 10 volts. The potential of the joint D is to be found, that is one of the options there, and the currents in the segments AD, DB and DC are also to be found, because he has given you the ratio of the currents in AD, DB and DC. And then we are also supposed to find out the net power drawn by the circuit. And what is the formula you are going to use for finding the power? I square R. So, once you find out the current in this and this, you can simply square the respective currents and multiply by the resistances to get the total power drawn, right. So, what we will do here is, we will imagine that the current flowing in this branch to be X and the current moving towards this joint to be Y, and by your junction rule, if the incoming current is X and the outgoing current here is Y, the current which has to go in this branch is X minus Y. I hope you agree with that. Okay. So, now I will simply move from A to the point D, taking into account the potential drops. So, I started from the point A where the potential was 70. I am moving in the direction of the current, therefore, there is a potential drop there, and I am supposed to write it as current multiplied by resistance, that is 10x, and then I have reached the point D where the potential is, say, V. 70 minus 10x is equal to V. Now, I will move from V to this point. So, V minus 20y equal to 0. See, V minus 20y equal to 0, and similarly V minus 30 into x minus y equal to 10. Fine. So, these are the three equations that you got by simply moving from A to the point D, D to the point 0 volts and D to the point 10 volts, taking into account the potential drops happening in the resistances because of the currents. Okay. So, 70 minus 10x is equal to V, where V is the potential of the point D that I am supposed to find out, and then V minus 20y equal to 0, second equation, and V minus 30 into x minus y is equal to 10. Now, there are three unknowns and three equations here. See, x, y and V are the three unknowns and three equations. If you solve them, you are going to get the potential, firstly you are going to get the currents x, y and z, or x, y and x minus y, and that will happen to be 3:2:1. So, this option is also correct. And then if you substitute the value of x in one of the equations, you are going to get the value of V there. You get the value of x to be 3, I think. So, 70 minus 30 is going to be 40 there. So, the first option is also correct. Three unknowns, three equations. I hope you agree. If you solve them, you are going to get the values of x and y and x minus y also. That happens to be 3:2:1. And if you put the value of x here, you are going to get 70 minus 30, which is equal to V, and that is 40. That option is also correct. And now, if you try to find out the amount of power which is drawn by the circuit, see, let me show you. The power drawn by this resistance is going to be 3 square into 10. I square R is what I am using, 9 into 10 plus y will be 2. So, 2 square into 20, 2 square into 20 plus x minus y will be 3 minus 2, which is 1. So, 1 square into 30, and that makes it 90 plus 80 plus 30. 90 plus 80 is 170, 170 plus 30 is 200. So, 200 watts will be the power drawn by the entire network. So, that makes your option D also perfectly correct. See, I took this problem particularly because there were more than one options correct in this particular problem. So, here is one more problem. See, he has given you a network and he says the potential difference between the points A and B is 16 volts, and he wants you to find out the current which is passing through this 2 ohms resistance. It is an open network. There is a potential difference between A and B given to be 16 volts. So, current will flow from higher potential to lower potential, and here there is a closed loop also. So, definitely there will be a current. So, he is asking you to find out the current through 2 ohms resistance. Fine. Okay. So, let us first imagine that we are going to take the current as X in this. And the current which is to be found in this 2 ohms is say Y. So, by the junction rule, if the incoming current is X till this junction and Y is the current which has flown here, the current which must have continued here should be X minus Y. And then this Y comes to this particular junction again, X minus Y will have reached. So, X minus Y plus Y will make the current which will continue here to be X. So, I hope the marking of the currents are fine, right? I hope you have understood that. Okay, now we are going to form some equations. One equation will be directly by moving from A to B. So, I will start from the point A, call the potential to be VA there. I am moving in the direction of the current, so there should be a potential drop, and drops are written as negative. So, it is minus 4x, and then I am crossing this battery and I am moving from positive terminal to negative terminal. So, there will be a potential drop again, and that has also to be written as minus. So, it is minus 9 volts. Then I am coming across this resistance in which the current is X minus Y, and I am still moving in the direction of the current. So, it is minus X minus Y. See, there is a drop, so it is minus. So, minus X minus Y. Then plus 3, because I have moved from negative terminal to positive terminal. So, there is a potential rise. See, here I had moved from negative to positive, there was a potential drop, and here I am moving from negative to positive. So, there is a potential rise. I am still moving in the direction of the current. So, it is minus 4x, and now I have reached the point B. So, it is equal to VB. And remember, VA minus VB is given to be 16, because he says potential difference between A and B, that is VA minus VB, is 16. So, if you write that 16 and also simplify a bit, you are going to get 16 minus 4x minus x is minus 5x, minus 5x minus 4x is minus 9x, then plus y, here see minus of minus plus y, and then minus 9 plus 3 is minus 6 equal to 0, and that gives you 16 minus 6 as 10. So, y minus 9x plus 10 equal to 0. Y minus 9x plus 10 equal to 0 is your equation number 1. Now, just take this particular loop here and then write one more equation in x and y, and then let us solve them simultaneously and get the values of x and y. Okay. Now, if you just go around this particular loop, say starting from here, negative to positive plus 9, negative to positive plus 9, in the direction of the current minus 2y. See, I am travelling in the direction of the current, there has to be a potential drop given by your IR, I is y, R is 2, and then I am coming opposite to the direction of the current. So, plus resistance is 1 and current is x minus y. So, one loop is over and the sum should be equal to 0. The sum of the potential drops and potential rise in a closed loop taken together should be equal to 0. So, 0. Now, if you solve this, x minus 3y plus 9 equal to 0. So, if you solve these two equations simultaneously, see this is equation number 1 and this is equation number 2, you are going to get the value of y as 3.5 amperes. So, that makes your option B perfectly correct. So, here is one more network. See, the purpose of taking all these problems is to just let you know how to analyze the network. See, in couple of problems I think we moved from one point to another point, taking into account the potential drop and the potential rise, and I wanted to highlight that if I am travelling in the direction of the current and I am passing a resistance, there is going to be a drop in the resistance given by your Ohm's law V equal to IR. If I cross a battery, what am I supposed to do? If I move from negative terminal to positive terminal, I should have to consider it to be a rise, and rise is written as positive. If I go from negative to positive, there is a rise, and from positive to negative there is going to be a drop. So, I do not know if I said correctly earlier, but so I just wanted to tell you that while moving from one point to another point and coming across these circuit elements, how are you supposed to take the drops and the rises, and how are you required to write them. So, here is one more network which I am trying to analyze. See, he says there is a cell which develops the same power across two resistances R1 and R2 separately. So, when that cell is connected to the resistance R1, the power developed, and when the same cell is connected to resistance R2, the power developed is same. Find the internal resistance of the cell. So, which means he has clearly told you that the cell has got an internal resistance and you are supposed to find it out. So, what we will do is, I will first try to find out the current flowing through the network consisting of one cell and one resistance, and that will be E divided by R1 plus small r. So, this is the current. So, how do you write the power developed across a resistance? I square R. Fine. So, I square and then R. This should be equal to again I square into R. See, what was the simple circuit that I had imagined? See, this battery with this resistance connected, and remember the EMF of this battery that I have taken is E and the internal resistance is R, and this resistance is once going to be R1 and the second case it is going to be R2, because both the resistances are to be separately connected across this cell. So, once the current will be E divided by R1 plus R, and the next time the current is going to be E divided by R2 plus R, and current square multiplied by the resistance will always give you the power developed across that resistance. And because he says the developed power is same, I have equated. Now, E square gets cancelled and you get an equation like R1 by R2 is R1 plus R divided by R2 plus R whole square. Now, if you solve this equation, or let me simplify you one more step, it will be R1 plus R divided by R2 plus R equal to root of R1 divided by R2. So, I have taken the square root on both the sides, so it is root of R1 divided by R2. Now, you cross multiply or you try to simplify this using your componendo, dividendo or whatever, but if you simplify this and solve, you are going to get the value of small r as root R1 R2. So, that makes your C option perfectly correct. See, we have all heard about this maximum power transfer theory, wherein I think you will have remembered that when the external resistance becomes equal to the internal resistance of the battery, the power transferred to the external resistance is going to be maximum. Fine. So, this idea we all have, but see, this is the beauty of the problem given here. There are two batteries with two internal resistances. So, one battery is of 10 volts and the internal resistance is 1 ohm. This is also an identical battery. Both are connected in parallel and across the resistance capital R, and he wants you to find out the maximum power developed across this resistance R, right. So, I hope you realized the importance of this particular question. Had there been only one battery with internal resistance and one external resistance, you would have directly used your maximum power transfer theory, saying that the external resistance should exactly become equal to the internal resistance, and then you could have written the power, right? Power is I square R. So, find out the current and square it and multiply by the resistance in which you want to find out the power developed, and that power would have certainly been the maximum power. But now you have two batteries. So, here through this problem I would like to let you know the formula which will help you to find out the equivalent EMF of one single battery and equivalent internal resistance. Fine? Okay, so let us do that. See, the formula which gives you the equivalent EMF will be sigma E by R divided by sigma 1 by R. Fine. So, this is the formula which gives you the equivalent EMF of that single battery. Okay. Sigma E by R, the summation E by small r. E is 10, small r is 1. So, 10 by 1 plus one more 10 by 1, fine, divided by 1 by 1 plus 1 by 1. So, that gives you 20 by 2, which is 10 volts. So, what is the equivalent EMF of that battery which you are going to replace from these two? The equivalent EMF is going to be 10 volts. Fine. So, now let us find out the equivalent resistance. See, there are two internal resistances which are connected in parallel, which makes their equivalent resistance small r, or you can say small r naught, as half. 1 into 1 divided by 1 plus 1. I hope you remember the formula for finding the equivalent resistances of two resistors connected in parallel. Fine. So, that is 1 into 1, R1 into R2 divided by R1 plus R2, which makes it half. So, now you are ready with an equivalent EMF, say E naught, and equivalent resistance, internal resistance half, connected with an external resistance capital R. So, your new circuit is simply like one battery with one internal resistance and one external resistance through which you want to maximize the power. So, this is R naught, this is E naught, and this is capital R. And now you can use your maximum power transfer theory, saying that when the external resistance becomes exactly equal to that internal resistance, or capital R value becomes equal to half, then the power transferred will be maximum. Okay, so what I will now do is I will simply write the current in the network, then I square R will give me the maximum power. Okay, how do I write the current? 10, that is EMF, divided by half plus half is 1, right? So, this is the current. See, 10 is the EMF, and divided by the total resistance of the network is half plus half, that makes it 1. See, this R has to become equal to R naught for the maximum power to be transferred. So, half plus half is 1, so that is 10. So, 10 square multiplied by the external resistance through which the power has to be written is half, and that makes your answer 50 watts. So, first option is perfectly correct. So, another simple network here, but the purpose of taking the problem is to let the student understand about earthing. See, whenever you see a connection with the earth, you can always take it for granted that the potential has become 0 there. So, a connection to the earth assures you about the potential at that particular point. So, here is the network. See, the switch S is closed, connecting this particular point to the earth. So, which guarantees you that the potential of this particular point will become 0, and then he wants you to find out the current which will flow through the switch. See, as long as the switch is open, there is no scope for the current to flow in this 2 ohms resistance, because there is no outlet for the current to flow. Switch is still open, remember. Therefore, there will be only a current flowing through this 2 ohms and 4 ohms resistance, reaching the 5 volts junction from 20 volts, making these two resistances in series. A current directly flows from 20 volts to 5 volts, making the two resistances 2 and 4 ohms to be in series. Fine, but the moment you close the switch, there is a scope for the current to get branched at this particular junction. So, what we will do is, we will first try to imagine the current. Let the current in this particular arm be X, let the current in this arm be Y, and let the current flowing through your switch be X plus Y. but I hope you are convinced with the direction of the current that I am marking. Let me tell you that these currents are just the imaginary currents which I have marked. Their directions are also still unknown. Magnitudes are of course not known. So, but what makes me show the direction in that way? A small simple argument is current always flows from higher potential to lower potential. This is 5 volts. So, I thought the current should be coming from 5 volts trying to rush towards the 0 volts junction, and here the potential is 20. Therefore, the current must be coming from 20 trying to rush towards the 0 volts potential. Just a feeling, even if you mark the currents in the opposite directions and solve, still it is going to be fine, because neither we know the magnitudes of the current nor the directions of the current. But be careful about what current have you mentioned through the switch, whether it is x plus y or x minus y. Accordingly give the answer. Fine? Okay. So, now I will just move from one point to another point. Say 20 minus 2x plus 4y, 20 minus 2x, I hope you agree with this. See, I am moving in the direction of the current in the resistance, therefore, there should be a potential drop, and that is given by IR, so minus 2x. Here I am moving opposite to the direction of the current and crossing a resistance, therefore, there should be a potential rise given by y into 4 equal to 5. So, that gives you minus 2x plus 4y equal to minus 15. So, this is your equation number 1. Fine. Minus 2x plus 4y equal to minus 15. That is your equation number 1. Now, if you just move from say here till here or like this, you get 5 minus 4y, 5 minus 4y in the direction of the current, minus 2 into x plus y equal to 0. See, here also you have travelled in the direction of the current, and here also you have travelled in the direction of the current. So, in both the resistances there is a potential drop which is addressed as negative, and this equation will be 5 minus 4y minus 2y makes it minus 6y minus 2x equal to 0, and this is your equation number 2. Fine. So, now you got your 2 equations in x and y and 2 unknowns. If you solve them simultaneously, you will get the values of x as well as y, and then your answer is going to be x plus y, and that leads to the first option, 4.5 amperes. Of course, you can always verify solving these 2 equations simultaneously and getting the values of x and y, but remember the current through the switch is x plus y, and that is 4.5 amperes. So, the purpose of taking this problem here is also to make use of our knowledge about earthing. Just now I had told you that whenever you see a connection to the earth, you can consider the potential of that particular point to be 0. See, here is a network, and he says you have to find out the net resistance or equivalent resistance between P and Q. Of course, it is a problem on finding the equivalent resistance and quite simple also, but still I have taken this because there may be a confusion among the students here of this R and this R not being connected. Fine? Okay. But please remember that this R is also connected to the ground and this R is also connected to the ground, and ground being a conductor, it is as good as telling you that these 2 R's are directly connected to each other. That was the beauty of this particular problem, and I took this problem just for that reason. See, this R is connected to the earth, this is also connected to the earth. So, indirectly he has assured you that these 2 R's are directly connected to each other. So, let me redraw the circuit once again. So, this is one R, another, and these are your points P and Q, and here you have these 2 R's connected directly to each other. See, this R connected to the earth and this R connected to the earth will make 2R connected to this single wire, R and R. Fine. So, this is the simplified network, and you are supposed to find out the equivalent resistance between P and Q. Now, just imagine the paths that you have in reaching from P to Q. So, here from P you go to Q via this resistance, there is one more path through this resistance, and there is one more through these two resistances. So, these two are in series, and then the three paths are in parallel. So, R, R and 2R. So, your equivalent resistance between P and Q will be 1 by R equivalent equal to 1 by R plus 1 by R plus 1 by 2R. 1 by R plus 1 by R is 2 by R. So, 2 by R plus 1 by 2R makes it 5 by 2R. See, 5 by 2R, and that is 1 by R equivalent. So, R equivalent will be 2R by 5, and that makes your B option perfectly correct. And I hope you enjoyed this problem. So, one more problem here on earthing and a simple network connected with that. So, let us read it. See, this is the network he has given, and A is also connected to the earth and B is also connected to the earth. So, which by our previous knowledge we have understood they are connected to each other. Select the correct alternatives, he says. VA minus VB is 0, VA minus VB is something, that is E. IAB is 0 and IAB is something. So, those are the options which are given. Fine? Okay. So, what we will do here is, first, having understood the concept of earthing, I think we can directly pick up one of the options there. See, A is connected to the earth, so the potential of A should be 0. B is connected to the earth, so the potential of B should be 0, and therefore VA minus VB should be 0. Right? VA minus VB is not E, VA minus VB is 0. That alternative can be selected without any problem, just using the knowledge of earthing. Fine? Okay, but I think now the beauty of this problem is, a student who has picked up VA minus VB equal to 0 or VAB equal to 0 may feel that the current which is moving from here till here is 0, because when there is no potential difference, why should the current flow, is what he may superficially feel. But remember, if there is a potential difference somewhere in the path, then the current is bound to flow. And somewhere in between, if you come across a zone of no potential difference, current cannot simply stop, because the current has been flowing in that particular circuit because of the potential difference that it has found somewhere, and then the flow cannot all of a sudden come to a halt only because some areas do not have any potential difference. Fine? Okay. So, let us redraw the circuit and understand why is that there can be a current from A to B in spite of not having any potential difference between A and B. Fine? Okay. So, I will redraw the circuit. Now, I will use my previous knowledge here, wherein I had shown you that when this is also connected to the earth and this is also connected to the earth, they are indirectly connected to each other. So, I will redraw the network here, see. So, this is your battery of EMF E, this is the resistance capital R, they are connected like this. So, there will be a current flowing through this branch, and he is asking you to find out that current. Let us assume that the current is I. Now, I will simply go round the loop and I will try to find out that current. Fine? Okay. So, plus E, because I am travelling from negative terminal to positive terminal and there is a potential rise, and here I am travelling in the direction of the current, so there should be a potential drop. So, minus IR should be equal to 0, and that gives you the value of I as E by R, and that makes your option D also perfectly correct. Right? Of course, you may always get problems of single choice, but I thought this problem was beautiful for this reason. That is the reason I had taken this in spite of two options being correct there. I hope you enjoyed this problem. So, please remember And one more thing is, this resistance which we show isolated is simply not isolated, or you cannot imagine that the resistance is present only in this localized region. It is basically the resistance of this wire forming the entire network. And that also helps you understand that even when there is no potential difference between A and B, the current can flow, because the resistance here is not localized, but there is a continuous resistance in the entire path. I hope you realized this. Fine. So that's the beauty of the problem. Current is E by R and potential difference between A and B is 0.